This video is about a small it's about comparison between the kernels computed using sw4 and that computed using AWP for a half space surface wave example, the LAMB problem, LAMB problem. Maybe I pronounced it wrong, but it's a half space problem with uniform half space velocity model with source and receiver located on the surface of the uh, half space, and um, I'm doing a comparison of the surface wave kernels at two different frequencies. So the problem setup is kind of similar to the LAM problem explaining SW4's user manual. So uh, that's the directory where I'm doing the comparison on Tton, right? So I got two directory AWP and SW4. So inside of the sw4 directory, I have a problem setup. So the box is specified by these lines of codes. That's like the dimension in the x direction is 20 kilometer, and then the dimension in the y direction is 40 kilometer, and then the thickness of the model is 20 kilometer, and then the grid spacing is 50 meter. I'm computing synthetics for up to like 27 seconds, and then with this kind of structure model. So the grid spacing is kind of uniform. It's 50 meter grid spacing, and I also tried a few different configurations with the sw4 refinement command, but those things were not particularly. The results were pretty much similar, so I didn't actually use a composite grid. So here inside of sw4, I'm just using a uniform grid, and then there's a few new capabilities that I added to the code. One is that for sw4, I can specify the x and y, the 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 starting and ending region for storing the kernel, or for storing the strand fields. So XREC-B, that's like 5 kilometer, and XREC-E, that's 5 kilometers. So in the x direction, I start to save the strand fields at from 5 km from 5 kilometer to about 5 kilometer before the 5 kilometer before the end of the x direction, and then in y direction I'm starting to save at the 6 kilometer, and then stop saving at 6 kilometer before the end of the largest y, and then in the z direction I'm saving up to down to like 10 kilometer depth. So this kind of a range for saving the strand fields is a kind of new capability, and then the spatial decimation rate is kind of similar, and then the time decimation rate here I'm specifying as 10, and this is actually quite large, so there will be some consequences in the kernel. So one of the problems with the kernel is this kind of a small chattering in the kernel, right? So this is the sw4 kernel, and then this is AWP kernel. The AWP kernel was saved on with the decimation rate. Oh, it's also 10, but the time sampling rate, the time decimation rate is 10, but the time step size is slightly smaller than this one. But this kind of small chattering is caused by a temporal decimation rate that's kind of too high. So if I reduce 10 to like 8, then this kind of a small chattering is gonna disappear. This is high frequency kernel, so you can sort of see the chattering becomes more severe. But at low frequency, the chattering is kind of less severe. So this is a new capability, right? This is a new capability, but this capability is not available for AWP. So for AWP, I still have to actually save the entire grid. The recording grid is kind of the boundary of the recording grid is kind of similar to the simulation grid. So it doesn't allow us to actually save in a sub region or sub volume inside of the entire simulation domain. Um, and then that's the source receiver list. I got like two different one source and one receiver, but both of them can act as a receiver. Both of them can act as a source because it's a Green's function. So P1 is located at um, about 10 kilometer. P1 is located at is it P1 is located at about 20 kilometer from the P1 is so P1 is probably 10 kilometer by 10 kilometer in the on the surface, and then P2 is located at 10 kilometer by 30 kilometer on the surface, right? So the distance between them is like 20 kilometer. Um, and then I'm using this particular source time function. It's a low pass filtered Butterworth filter, order 6 with a cornet 1 Hz. Right? I've tried different source time functions. I tried fourth order. If I use fourth order, then the synthetic seismograms have too much of a high frequency component for the surface wave, which is caused by numerical dispersion. I think I don't really know, but I suspect it's numerical dispersion is kind of too severe. So I cut it to like I increased the order to like 6th order. And then the corner is at 1 Hz. That's pretty much the two most important input file for the sw4 simulations, and then the synthetic seismogram for sw4 is gonna look like that, look like the blue curve here. What actually surprised me is this kind of a reverse dispersion effect, right? So high frequency actually arrives earlier than low frequency. So at the beginning of the radio wave pulse, you sort of see this kind of high frequency oscillations, right, which may have caused this kind of a unusually large onset, right? This downswing is kind of a might be too big. I'm not sure, right? And this kind of oscillation does decrease if I reduce the grid size. So suppose I add a refinement in the input file, right? So I can refine the grid from like a 50 meter to like 25 meter. If I do that, these kind of small oscillations in front of the radio wave is gonna sort of reduce, right? And if I reduce the grid spacing by like 2 more, a factor of 2, again to like 12.5 meter, then this kind of oscillation is gonna become even smaller, right? And this effect is somehow surprising because I thought SW4 is supposed to be more accurate than AWP. So the red curve is actually synthetic seismogram computed by AWP. It doesn't have this kind of small oscillations in front of the radio wave pulse. It has some small amplitude oscillations behind the pulse, but in general, those kind of numerical stuff is kind of small for AWP for this radio wave example, right? So it looks like the radio wave computed by AWP is slightly more accurate if I am using the same grid spacing, right? So for SW4 it's 50 meter, and then for AWP it's also 50 meters. So The grid spacing is 50 meter for both cases. But the synthetic southern one seems to be slightly more accurate for AWP. Right, the red curve is slightly more accurate at the beginning of the southern one, at the beginning of the relay wave pulse. But there's one more thing that I want to talk about, which is actually the amplitude. So here there's another sort of change to the source receiver input file sr/lst. So now for body force, I have instead of just the three numbers, I have one more number, which is actually the scaling of that body force. And then for moment tensors, it's gonna be 6 numbers plus 1. It's gonna be 7 columns, and the last column is gonna be the scalar moment, right? So if I want to look at maybe HS, AWP jobs, SR info, SR LST. So that's the 6 numbers for the moment tensor, and then there's a scaling for the scalar moment. Right. Again, for this is the 6 numbers for the moment tensor, and then a scaling the scalar moment. Right. It's the same is true for the let me look at the sw4. So I forgot to actually change that. Right, so I'm supposed to actually change to add one more column to the. Oh, this one has added. So the scalar moment is this number, right? The 6 numbers here is like the moment tensor for the explosive source, and then this one is the scalar moment, right? And these 6 numbers are for the moment tensor, and then this is the scalar moment, right? And then for body force, this is the scalar moment. So that's another thing, right? So, but if I compare the that's for the half space example, right? For the Lamy example, for the Lam example, it's so that's the input for sw4, right? But if I do a cat of AWP, you sort of see the scalar for the body force is differ by a factor of 2 for the AWP. So for AWP, in order to get the correct kernel amplitudes and also the synthetic southern wire amplitudes, I have to double the strength of the body force for the 2 surface sources, right? This is not the case for the source that was buried. Right. For the half space example, both 1001, both this source and this source are buried, right? And also the receiver was buried, and I didn't have this kind of scaling problem, right? Because for the green tensors, the scaling was 1, right? For the AWP case, right? But for the surface case, for the surface kernel, for the surface example, the Lam example, I have to actually multiply the strength of the force by a factor of 2 for the AWP case, right? For surface kernel example, for the Lam example, right? So for sw4 the strength is 1, but for AWP I have to actually multiply the strength by 2 in order to actually get the kernels to have about the same strength, about the same scaling, the amplitude. I mean, about the same amplitude. And then the synthetics are gonna be have about the same amplitude, right? So if I do not change the strength to like 2, then the synthetic southern one is gonna have a amplitude that's about half of that for the sw4 case, right? This was a problem when I was dealing with surface wave or ambient noise data in AWP, right? But by doing this comparison with sw4, it becomes more obvious what I'm supposed to do in order to actually make a correction to the problem, right? It looks like if I multiply the strength by 2 for the body wave, for the body force source, then the kernel is gonna look pretty much the same with a similar amplitude and a similar um, shape, right? Um, but uh, mm, okay, so I'm not sure there's anything else I want to talk about, but that's the surface wave kernel example that I have been doing. This LAM experiment um, was documented quite well in sw4's user manual, right? So here is I'm in the AWP directory, and then if I do a cat of the parameter file, um, so dt is slightly smaller than the dt that's computed by sw4. And then anti-skip is for AWP is 10, right? Um, and all the shell scripts and all the commands that's needed in order to actually run the entire experiments are kind of documented here inside of this jobs directory. Yeah, that's the LAM experiment. Um, for this kind of small chattering, if I change my um, so if I change my input file, right, to the previous one, and then run it again, uh, that's even bigger decimation rate. So you sort of see this kind of chattering becomes more severe. Even it actually goes to the low frequency kernel also. And then if I go back one more, I was still doing the same kind of experiment, but right, that's even more severe problem, right? And then 7, right? For 7, it doesn't have this kind of problem anymore. So that's because the temporal decimation rate was changed back to the correct one. Right, so this one has pretty similar shape with the AWP result, right? But for some reason, the AWP kernel looks like it's kind of a, how do I say? The cross section looks thinner for some reason. I have no idea why, but it might be just a few layers on top was kind of missed because the spatial decimation is like 4, right? In the vertical direction, the spatial decimation rate is 4, right? But sw4 is gonna save the first layer on top because the vertical direction is like points downward, right? So the first point is on the surface, and the first point is always saved. So that's gonna give AWP sw4 kernels maybe one more layer on top, I think, right? But for some reason sw4 AWP is actually saving from the vertical direction is pointing upwards, right? Uh, so maybe the top layer was kind of missed because of the sampling. Um, and yeah, I think that's a pretty meaningful comparison, and I have learned quite a lot by doing this experiment. It's and I've added a few more capabilities, right? So one is that the sw4 now the kernel code for sw4 now accepts a range for the recording grid in x, y, and z directions. And then the source receiver input file now takes a scalar moment and a scalar body force in order to actually scale the moment tensors and also the body force vectors. That's like the two most important changes I've made so far for this particular experiment. Okay, so that's it for this video.